so let's start. The topic that we will cover today is on speech signals and the concepts of how speech is produced from speaking, obviously, but how does it work? How does speaking work? And also about perception. So it means that what we will cover today would be in terms of the anatomy and mechanical function of speech generation. That means we will touch upon a lot of physics and actually biomechanics, right? So if you are not sure or if you don't understand on any of these topics, please feel free to ask me right away. Right? I love discussion, so we can have discussions during the class, and that would be nice. All right. It's just 20 of you guys here, so well, discussing would be fun. Okay. And and also if you are not sure what I'm talking about exactly, some of these might be the topics that you may have not studied or you may have not been exposed to before. Feel free to again stop me and then ask about those basic concepts. I can try to explain to you in the layman term, so at least we can continue and then you might grasp the concepts out of that, right? So speech processing is actually an interdisciplinary, which means that it is a discipline, it is a multidisciplinary, right? It is a discipline that requires you to combine knowledge from different science, different parts. Some of them are from the science, some of them from arts. For example, in my study, I have to study about language, about linguistics, about phonetics. And my colleagues at University College London back then, they were some of them were phonologists, phoneticians, which means they are actually linguists, those who work with language, rather than engineers that work on the computational and application part of the speech processing. So in order to make a successful speech processing software, you need to understand on both sides of this, not just on the engineering, but also on the linguistic, on the language part as well. Okay, so let's begin our journey to understand speech signal. When you capture speech data using computer, what you get from those files when you open with the digital audio workspace, or whether you want when you open it with the audio editing software, or even play it on a computer, the data stored in those files can be translated, can be displayed in the time domain as this signal. This is what speech signal look like in time domain. This is my recording. I think I need to dish off the light. Yeah. Testing. Right. Do you hear the my voice? Because I'm not sure. I did share the sounds though. You should hear that, right? Good. Okay. So that testing can be plotted into a time domain that looks like this, right? This is the time in seconds, and you can see that the word testing occupy only a brief less than 1 second. This is 776 milliseconds. Okay, and you can see that here. So the x-axis would display the time that that change through the voice changing, through the vibration changing here, right? And the y-axis, that you can see here, you can see that it is not quite symmetric. It depends on a lot of things. It depends on the recording. It depends on the microphone that you use. It depends on the type of medium that or the types of vibration that you try to record. And it will produce, well, pretty much the sounds would look like this. that would be swinging around 0, but the symmetricity can occur depending on the types of recording equipments that you use, the types of sounds you try to record. The height of the signal here that you see is the normalized value captured from the process that we talked last time. Okay, if you use 16-bit recording, that means suppose that the maximum audio here is 1 and down here is -1. Actually, it should be minus here, -1. Then it means the variation can range from 1 to -1. That's these are the extrema, the maximum and the minimum values that it can goes. For that 1 and -1, if you use just, let's say, 2-bit to encode data, then you have only like 4 steps. But if you use 16-bit, is the number of steps is actually 2 to the 16, right? 24-bit recording is 2 to the 24, right? So that is the available steps that the value here can take. You can see that with 2 to the 16, you have 65,000 steps, which if you convert that into -1 and 1, well, that is quite a lot, because you can imagine that when you take a small step here, you might not even notice that this value is one step which is different from another one. Right. So that is for the bit when you store data. For the bit rate or the sample rate, that's for the bits, the bit size, the size of the sample size. Right. So for the sample rate or the sampling rate, this is the rate of which you want to record the data. It can be 44.1, it can be 48K. And those will be the number of points that you want to gather in 1 minute. Why would you want to have higher value like 192K? If you want to record something like that, that would mean you have some types of sound source that generate the data beyond human capability of speaking. And that is quite possible. If you record, for example, the musical instruments, the harmonics might exceed 20K. And if you want good quality sounds, you might want to capture those, although you might not be able to hear them though. And also, remember, if you have when you play the sounds, it depends on the types of the output equipment as well. If you use speakers or headphones, those speakers and headphones also have the frequency response that will tell you that those equipments can generate the sound from minimum frequency to the maximum frequency. So make sure you understand those so that you know that each equipment would have like different limitations. But yeah, in recording, the sample rate would dictate the number of points. Okay, so for 0.776 milliseconds, this is from 34,000 data points, quite a lot actually here. And the testing in time domain, and if you take a look at this picture, what you will see is that, well, I think one thing is that the mouse size is quite small. Let me increase the mouse size. Mouse size, pointer size. Yeah, this should be better. No, not in the display though, but in my computer it's fine. Okay, so what I want you to notice is that there is certain patterns that you can observe through your eyes, like the testing sounds. The t sounds has this pattern, and it's not quite periodic. The a sounds has quite a periodic pattern. and the sounds here looks like the th, and again test, the th sound again here, and ing. Right, you can see that there are certain periodicity here, but how comes they have different patterns? And if we were to process these sounds, then it is our job to understand why is this the case, right? Why some sounds has this pattern, why some sounds exhibit periodicity. That is what we are going to look at today. Right. First off, when you see this speech sounds, the thing that you will first notice, it would be something like, hey, there is a certain pulse like signal here. That is, you have like a certain one pulse here, another pulse here. Right? What are they? Right? This is a basic unit called syllable. Like syllable in Thai is translated as payang. Right? And we usually in Thai, when we learn to speak, we usually just learn this in the textual format. That this is like half syllables, you have to pronounce correctly. This is full syllables. But in speech, syllables is a unit that when you can see that it's a unit that associate with language like that. And it is in terms of linguistic, it also has certain sounds, specific phoneme, specific structure related to them. Like it must have initial consonant. Initial consonant is the initial, right? The consonants mean payanchana in Thai, right? And it must have vowel, sara, right? The vowel. And when you combine them, it forms syllable unit. Like when I speak something like ma, or this testing, right? The test and the ing forms two syllable here. Okay, this is another recording, my recording. The software that I use to record this, I will show you later on this for today's lecture, because you have to use it to do the assignment 1-1, which will be given out today. Which will ask you to perform analysis of speech and also produce your own voice and analyze your own voice. Okay, so here it is, me and nam, right? When you speak all together, you have this me nam. And what you can see is that when you pronounce me individually and nam individually, the words seems like it looks longer, and it is longer when you take a look at the time it occupy the word me and the time it occupy the word nam. Right? Some of you may have seen this infographics that show that there are different speaking rate in different language, and Thai is among the slowest. It's like when we speak, it sound is when we speak, the rate of syllables coming out is slower than the other language. I'm not sure though. Well, it depends on the recording as well, whether they actually record the data from us normal speaking people, or whether they kind of conducting experiment and then doing that in the control experiment, which you can really deliberate pronunciation for Thai when you speak really slow, like me, nam, something like that. But you know, when we speak in Thai, usually we speak quite fast. But what I want to emphasize here is not that, is the effect of the stress and duration. The time it takes for one syllable, or the time it takes for each syllable to be pronounced, or each word to be pronounced, that time or that period of time is called duration. Right? Duration is a general word to refer to the period of time that occupies certain things, right? Like the duration that you visit your friends, the duration that you play games. Duration here is the time it takes for the duration I want to talk about here is the time it takes for each syllable to be pronounced. For the word me, it takes about 546 milliseconds for the word nam pronounced in isolation, in the isolated word manner. It takes 683 milliseconds. Combine them, แม่น้ำ right, and speak more naturally, you get different ratio, different compression, right? แม่ has been compressed. So it's not like we pronounce something like แม่น้ำ, right? When we pronounce the word แม่น้ำ continuously, what happened is that the initial word got compressed in terms of the duration, and the latter word, right, got elongated. How is that possible? Right? What happens here? This is the linguistic effect known as stress. That is in the language, in English, in Thai, there are certain way that when you pronounce the word, you would put the stress or I would say the stress into the syllable. For English, it is the mechanisms that would allow English speaking to maybe highlight different part, or actually to convey the correct pronunciation of the word, and can be used to distinguish meaning, right, for the word, like the word dessert and desert, right, which use similar pronunciation but different focus, different stress onto the syllable. But for Thai, the stress is occur in terms of the lengthening of the duration. This has been studied for quite some times, and it is a well-known effect here. But the effect will not be observable in pitch, which is the thing that you will see later on. Okay. So this is manam, which means that if you want to synthesize speech, you cannot just ask people to pronounce word in isolation and then just attach them together, right? Because there are certain temporal effects that occur in the natural speech. This is just one thing that you see, but there is also other things like grouping, like when you speak in utterance in the sentence, the middle one will be compressed and the terminal one will be lengthened. Right, you can try recording this yourself. You will see this effect quite obviously, and we do not perceive those actually. We perceive them as natural sounding, right? But we do not really hear the lengthening of the duration. That can be only observed when you pronounce them, and then record them, and then plot them to see what happened there. Okay, and the properties that is quite intriguing for speech is also the continuity. Right? When you speak, what really happened? Just try to speak. You are at home, right? So you can speak by yourself, and then you see that when you speak, the apparatus, right, the vocal apparatus, right, tongue, teeth, right, would move, and the jaw and lips would move continuously, and those continuous movements shape the vocal tract, right? Shape the cavity in your mouth. And what happened is that when the sounds coming out, it would be shaped in terms of the frequency content, and when they radiate out, the sound radiate out of your mouth, it has certain characteristics that also exhibit continuity as well. Take a look. This is อย่าว่าอย่างนั้นเลย right? I choose this utterance because it contains lots of continuation. อย่าว่า these are known diphthong, because when you control the mouth, it would close, but not that close like the word ba or pa, right? Those you need to fully close the mouth and then generate the sound. So ya wa yang is also the nasal sound, right? Which you do not close mouth, but you close the cavity inside between the, I don't remember the name, we'll see that later, close the cavity inside to generate the nasal sound, the sound that come out of your nose. Yeah, that is a sound coming out of your nose. That is why if you have flu or you got cold, and then you cannot really, and you got stuffed nose, then you have problems pronouncing those sounds like nga, ha, right? Because there will be blockage in the nose. You cannot produce sounds out of your nose. Yeah, sounds really coming out of your nose, right? So this is อย่าว่าอย่างนั้นเลย and what you can see here is this graph. This graph is the spectrogram, right? Spectrogram is a graph that show you the amount of frequency at certain times. This is from the technique called short time Fourier transform, which we will talk about that later. Short time Fourier transform. Right. The short time Fourier transform is how do I increase the font size? I can't. Never mind. The short time Fourier transform is a technique that capture the spectrum at each timing interval. The idea is that, well, let's go back to the previous slide. The idea is that suppose we have แม่น้ำ like this. To get short time Fourier transform, what the technique would do would be to have this window, right? This small window, and then say capture the data in this small window. It might actually be smaller than this, and then perform the FFT, Fourier transform, fast Fourier transform, and then you get like one array of data for this time period, and then continue doing that, right? Move the window a bit to this point with a certain overlapping, then perform analysis again, and then you get another array of spectrum at this time point, and keep doing that, keep shifting the window, and finally you get the results, you get the spectrum out like this one. There are certain control that analyzer can use, that we can use to analyze this spectrum. We can create a window we can create a spectrum that focus on frequency, or we can create the spectrogram that focus on time. So we can control both time resolution and frequency resolution. Like suppose we don't really care about the exact frequency band. We just want to know general energy where it belongs to, like this figure. But we want the resolution, a lot of resolution in time. So we can control that, like decreasing the size of window, and then it will produce that effect. Increasing the size will produce another effect. You get a lot of frequency detail, but less time detail. Right? So we will talk about that, I think, later on this lecture as well. Okay, so what I want to show you here is not that. What I want to show you here is in terms of the continuity of the frequency content. You can see here that there is the black part. The black part of the plot of the spectrogram is you can think about that as the main frequency, the frequency that contained in this speech sounds. These are known as formangs, right? Formangs can be they are known as formangs, which we will talk about that later on. Right, so these frequencies change by time, obviously. When you pronounce a word ya, right? Ya. You can see here that initially you got high frequency component you got a lot of energy, at this region, a lot of energy at this region. Afterward, the energy kind of moving down in terms of frequency component until it reach about this. This is the sounds of w when you pronounce that. And R again, you can see similarities between ya, the R in ya, and the R in wa, right? Both, well, it seems like this returns somehow to certain points. And yang, again, repeat similar pattern, but with messy frequency that is hard to detect here because of the nasal sound, like here, the yang pronounce when you pronounce that, there are certain the vibration come out of the nose, and also the maybe microphone that I use for recording kind of pick up the wind sounds. And ngan, right? And ngan here, the n sound, and löi. So there's continuity in spectrum, and that is resulting from us controlling the vocal apparatus, right? Controlling tongue, controlling the mouth movement. Well, if you have question, you can type away to I can answer that as best as I could. Right, now let's drill down, right, to see inside different sounds. So for this speech signal, we are going to zoom in into just a few 10 milliseconds to see this pattern, right? This is just about 40 milliseconds, right? 0.15 to 0.19, about 40 milliseconds for this windows. If we were to zoom in into just this 40 milliseconds of this sound, this is an A sound, right? In testing, what you can notice from this A sounds is that there are certain similarities, right? And there are certain patterns in this graph. And those patterns can be observed from, well, obviously, that valley, that's low point, right? It happens like 1 low, 3 high, 1 low, 3 peak, 1 low, and 3 high. Again, 1 low and 3 high, right? The patterns repeat itself, although they are not exactly the same, but generally, they look quite similar to one another. And in signal processing, right, we know that when you got a wave, it can occur in periodic manner, and we can measure the wavelength, right? The period that the pattern will repeat itself. Like in sinusoidal, you can measure the period, the t in sinusoidal, to compute the frequency, right, from of that sinusoidal. This as well, right? We can measure the time period of one pulse, and that is this measurement. This is the t here is the period of time, which is only 6.77 millisecond. Okay, how do I know? Actually, you can actually measure this using Pratt. This is quite amazing research tool. Actually, you can do it with a lot of software. Like you can use Audition, you can use Logic Pro, you can use a lot of audio editing or Audacity to perform to take a look at this pulse going in. Mostly people who use those software we used for producing, right, creating media. I also use some of those to my work here. But the Pratt is a free software that you can use it for research. Okay. I will introduce you to the program later on this lecture. And t is equaling to 6.77, which means if you inverse t to get frequency, you get fundamental frequencies of 148 Hertz. This is the fundamental frequency of the A sound that I pronounce. Okay, you can see that there are certain periodicity. Now, if I were to just capture the sounds, the S sound from testing, what would it look like if I were to zoom in? This one, I zoom into just 20, 30 milliseconds. And this is the patterns that you see from these sounds, from the sounds. These sounds, you cannot see any obvious periodicity, right, from the graph here. And that is because there is no, because of the mechanisms that these sounds are generated. They have to pass through a small slit in order, and then there will be a certain aerodynamics phenomenon happen, and that is quite amazing that we actually utilize those aerodynamics mechanism to produce the sounds in different patterns on different language, and then use them, combining them to do the communication. Okay, let's get to the point though. Okay, that's so the first one is for A, and this is for I. For the E sound, I think this is the E sound in testing. The E sound has larger fundamental frequency. If we were to measure from the valley to the valley, we got the T equal to about 10.74 milliseconds, which for this period can be converted to 93 Hertz. That is the fundamental frequency of the E sound. Right? Because, well, if you just listen to the word testing, right, and then you can perceive that A in test has higher note than thing, than in the testing, right? So you can you perhaps hear those numerically. You can also measure them as well. The frequency that you see is a part of the signals. We can think of these signals. Any types of signal actually can be decomposed into sinusoidal. That is the Fourier transform theory. Or I would say you can analyze frequency contents of any signal using Fourier transform. So what does it mean, right? It means that we are trying to think about any types of signal as the compositions of the multiple frequencies. For these signals, the signal that doesn't change, this is known as DC value. The DC value here will only have the constant value, no frequency. Frequency equals 0. And that means if we convert the data into the spectrum using Fourier transform, you get the peak value at 0 Hertz, right? The point 0. The sinusoidal, one sinusoidal here, will produce one peak at this point. If these sinusoidals were to be increased in terms of the frequencies by one-fold, we call that the harmonic of the signal. What we will get is that the frequency component would have energy at the frequency location of that point. Right? If you increase it by twofold, it will be 2 times of that initial frequency. We call that the harmonic frequencies. Okay, and the Nyquist frequency would be at the end point of the thing that you can record it. All right. So the technique that allow you to convert from the time domain to the frequency domain is called Fourier transform. For the data back then, if we were to talk about the frequency analyzers that can analyze the analog signals, the Fourier transform would probably have to be implemented on the circuit. Right now, mostly what we would do the discrete Fourier transform, analyze the Fourier transform using computer on the DSP chip on the program. And there is a technique that allows you to analyze Fourier transform. Actually, Fourier transform is quite complex in terms of computation because of this, right? Not because of the equation, but because of this e to the minus j omega, e to the minus j omega, or e to the minus j2 pi n. This is a floating point, and you need to kind of doing floating point multiplication lots of time, and this is quite complicated. The big O for this one initially would be like n square, but there is a better technique called fast Fourier transform, which doing something like this as well, but on a different strategy, so that and utilizing the periodicity of the exponent or exponential part. We'll see that later, but this course will not delve into how to compute Fourier transform though. That is for signal systems which you have passed those, or if you have not, I would suggest that trying to read something about Fourier transform. It will actually help you in working with the signal data, the time domain data, not just in speech, but might be in terms of, well, stock market, in terms of Bitcoin patterns, maybe, no, I don't know, or maybe in terms of other types of signals. Okay, right. So how does Fourier transform work? You are trying to decompose xk, which is the original signal that you have, into, well, not that, sorry. This is Fourier transform usually can be written in the two forms, synthesis form and analysis form. This is an analysis form. Analysis form, you have the xn here. Xn is the signal that you have. You need to multiply xn with the wkn for each k, right? Wkn is the projection signals that you kind of have a signal that is your original signal, and then you have wkn which have different frequency, and then you just multiply them together, and then see if they can be if it contains frequency at a specific region at the same frequency of this wkn, then it got values. If not, then value will be low. So with this technique, varying value of k from low value 0, 1 to the high value, depending on the number of points that you have in the analysis. You have the different frequencies, which different wkn, which when you multiply to the xn will produce different the energy at different frequency for you. Right? So that is actually the basic concept of Fourier transform. Multiply the signal, actually convolute the signal with the eigenvector at different frequency, and then see the energy, the remaining energy from that multiplication, and then plot the graph out. So this is quite slow in terms of computation because, well, multiplication here has to be done depending on the length of the signal. Then you need to summation, and then you need to run the index of frequency. Quite a number of loops there. Instead of doing that, there's a technique called the fast Fourier transform. The fast Fourier transform utilizes the divide and conquer technique and utilize the patterns of the wkn of the exponential to calculate the spectrum. So the basic idea can be explained in the pseudocode above and in this diagram. So from the initial time domain signal in the small letter here, if we take, there's a, what does n mean here, right? N, this N. Okay. What does N mean? N is the number of data point. Yeah. N is the length of xn. So what is this? This is the multiplication of the signal, right? Multiplication of xn with wkn at the at the specific frequency that you want to analyze. Say maybe starting from 0 and then 0 hertz, 1 hertz. Actually, it's not like that. Kn has to be according to the number of point and the sampling frequency. But well, it's just like that. You have different frequency value, and then you multiply it with the signal, like multiplying two signal together. And then you kind of sum them together, right? For sum them together, meaning that for this multiplication, you crunch them into just one number. And that is the representation of that frequency. And keep doing that from no frequency increasing iteratively to high frequency. And then this is discrete Fourier transform. And then you get the frequency component of the signal. Right. But that is slow. This is faster because it utilizes the property of Fourier transform, which I'm not covering that. Right? That is, well, well, you can divide the point and analyze them, and then there will be certain behavior. There are certain properties that you can combine them between even component and the odd component together to get the final one, which is faster. Well, I'm not covering this, but at least it's actually work faster than in the naive DFT calculation. The implementation of Fourier transform in computer relies on these concepts. Okay, now jump back. That's the technique that allows us to transform from this graph. Sorry, quite a while. From this graph into, not this one though, into this graph. This is the A sounds when you transform them into spectrum. X-axis would be changed from time domain to frequency domain. And how about the y-axis? The y-axis would indicate the amount of energy. Actually, it's called the magnitude of the Fourier transform. Right? Magnitude, or well, yeah, it's like the amount of energy occupying those band of frequency. Okay. For the A sound, we have, if you were to kind of look at it in the blurry way, don't just look at it in that is a kind of a ripple over, because this can be occurring from the thing that you see here, that there are certain like fluctuation in frequency domain. Sometimes this is from the windowing that we kind of capture just the A sound here, and without multiplying with the Hamming or Hanning windows, it would generate the ripples in the spectrum. This is the side effect of just taking some spectrum that Fourier transform cannot cope with. Okay, so when you take a look at this spectrum, you need to kind of looking it on something like the envelope of this spectrum, or just some trends that you can see from the spectrum. From this one, you see that there are certain peaks here. Right, the peaks at about 430 hertz, about here, and there is another peak here. If you go up and then go down, another peak here at 2580 hertz. These peaks at these two locations are the first and the second harmonics. First and the second harmonics frequencies. This is called formants, F1 and F2. Alright? And you can see that, the highest value is 2.8 205 to the 10 to the 4. This is 22,000 point. This number is really sounds familiar, don't you think? How does we get 22K in the frequency axis? Can anyone tell me? Yeah, you can turn on the mic or you can type. Both are fine. Why is it 22.05 kHz? Which is the maximum value? Why is that? Correct. That is the Nyquist frequency. Okay, good. All right, so the A sounds produce high peak, right, at different location, and you can expect that to occur for the R, the U, the E sounds. Right? They will have different locations, and those are very nice characteristics of human sounds, that human speech, that even though I'm male, about 40, when I speak the words A, you have the peak here. But for let's say the 20 years old female, if you pronounce the word A, actually F1 F2 will be close about this region as well. That is how we perceive the sounds. Is how we perceive the word. And then classify them as the thing that we hear. Okay. So it means that in order to understand speech, in order to understand speech production, understand speech processing, we need to dig deeper into the mechanism of speech production and understand them, not the perception part. Okay? The perception part is something that coming after production. In the production, you're trying to generate it out. Understand them will allow you to know why the patterns look like this, and can devise a way to cope with that. For the perception part, we have our brains to interpret the signal, which is unfair actually. Think about them as the deep neural network stuff that can perform complex recognition, and the ear can just perceive frequency, and then the brain will do the rest of the job. And if you want to model that, we will do that in the speech recognition, trying to do that as well. But we also try to do the old way. The old way is to capture the speech features based on speech production, and then using using machine learning, right, to recognize from the patterns. Okay, let's move on. Now, there are certain psychoacoustic of hearing. The term psychoacoustic refers to human psychology that are related to the acoustics data, or the acoustics part of the sounds. Human can hear only the sounds around 20 decibel. We can hear the sounds. This is the threshold of hearing. Right? The sound has to be louder than 20 decibel for us to hear. So it means that when we look at this graph, right, certain sounds we would not hear, like the sounds that are in this region. Right? We might not hear them because they have lower loudness. That frequency component would not be perceived by us. Okay. Now for the vowel that I'm talking about, there are actually a certain consistency in the vowel. This is the work that is done by Thai phonetician in collaboration with I think this is from Professor Abramson's work. He was the phonetician that worked on Thai. I think he is one of the founder of Thai linguistics back then, of the field itself. He worked with Ajahn Supaporn, which is the professor at Chulalongkorn University. That's Sudaporn, I think. And I read a lot of his work in Thai, because in Thai language, because those are very classic papers on Thai speech. Now there are works about Thai formants that if we were to plot F1, the first harmonic, first formant, and the F2, right? If we were to plot those graphs, we would have the values of different vowels occupying different region of the F1 and F2 axis. This is the E, right? About this is and U. They occupy closely to one another, but short and long vowels in Thai are isolated by the length, right? And also a little bit of the frequency there as well. And this is A, right? If you take a look at this, you can see that the mouths are kind of E, U, right? From having like line shape, right, to rounder. And this is the E to A to A to R. In linguists, they refer this to the front and the back vowels, right? The front side and the back side. And this is the high and the lows, right? The front, just try to imagine why it is called the front, like the E, and U. Why is that called in front? The constriction point, move from back to front, right? Like O, A, or the R and O. This is O, the R and O. And it's called high vowels and low vowel as well, because of the, actually just try to observe that, because I have the assignment for you guys at the end, observing your pronunciation and then explain what you observe as a result, right? From E to R. Why does it call high to low? E and A and A and R. You can just observe my mouse here, and then you might notice something out. All right. There is also the combination, right? Those are the static vowels. Static vowels are all the monotongue. Monotongue is like the vowels that you can kind of pronounce, and then it would just stay at that same level. Like if you pronounce the word R, it would be R for throughout that, right? The static vowel. This is more of the dynamic vowels, or the linguists would call this diphthong. In diphthong, you have to move from one vowel to another vowel, like from E to R, and then you get ear. From to R, you get From U to R, you get ua, right? And yeah, just try to pronounce that yourself, from ua. And when you pronounce that really quickly, you get ua. And what happened in frequency domain is the move of the energy from this region to this region. And that movement itself is the syllable, is the word that we hear. Right? Not just that frequency at specific point, but also the movement in frequency that allow us to perceive different sounds. Okay, now we call this fricative. Right? The fricative are the sounds that the fricative sounds. Fricative are just like friction. Right here, it's called fricative. Right? The fricative sounds are the sounds that contain the sounds like s, like s, f, sh. These are fricative sounds. The sounds that are not generated from vibration at the vocal fold, but from aerodynamic effects. For the S sound, this sound, okay, need to remove it. For this sound, this sound should occupy about 6 to 9 kilohertz, and it doesn't have any specific frequency, doesn't have prominent frequency, but it occupies about this region. The other sounds like sh, like f, would have different frequency as well. It would occupy different band of frequency. That's why you hear those sounds differently. Okay, now in recording, when you record the sounds, there is a possibility that the noise would be recorded. The old mic that I use, the Rode NT-USB, is good actually, but it has lots of noise. It is a condenser microphone, which means that it needs to receive electricity to control the vibration, and it is prone to receive the noise from the surrounding. It has to control. It has that's the problem of the condenser mic. Quite sensitive. It's quite good though, to a certain extent. This one has lower. It is dynamic microphone. Has a lower sensitivity, and it needs to have like the booster or elsewhere or other equipments, but it has low noise. These are called this noise. If we were to, if it's from not from air conditioning, if it's just like from electricity or from surrounding, we can think about them as the white noise. Right? These are the noise that is the random signals. And if we were to plot this signal in frequency domain, you would get this flat spectrum, right? There would be no prominent peak in the spectrum. It would be really low energy as well, but you can obviously hear them. Okay, so this is a noise. Yeah, this is white noise. Right, the noise from recording, the noise from other thing, the quantization, that would be different sounding though. Okay, now let's take a look at the other aspects of speech. Fricative, right? We take a look at fricative in the S sound, but there is also other sounds that is also fricative in English. In Thai, this is one of the problem when Thai when we try to speak English. We have problems with consonant because they are not taught in school how to properly pronounce English consonant. Even now, I actually learn from not learn from school, mostly try to repeat what I hear when I'm abroad, probably. but that is the weak point of us when we are the second language learner in English, because at school stress or intonation would not be taught, proper pronunciation of the consonant would not be taught, and also when you are not focusing on intonation, when you pronounce word to when you go abroad and then try to speak naturally, they would not recognize your word. Unlike the tourists that comes in, right? Tourists kind of has open mind that they would try to hear whatever you try to speak. But when you kind of go to go to Tesco in UK, and then you speak to the cashier, they would not care. They just try to go on their life. That means you need to speak good English, I think. But yeah, not many they will try to catch up with you anyway if they are open-minded. All right, no, whatever. Right. So English has different fricative. This is the weak point of Thai as well. And this different fricative, in terms of speech, occupy different spectral location. For the S sound, the sounds for male about this 6K. For female, this will be about 7,000K. The f sound and v sounds about this, and the th. In Thai, usually you pronounce it as the, but it's not. It's like thy, and it's there. It's like so that is the also fricative. The sh sounds has lowest frequency here. So different fricatives occupy different part of the frequency domain. That means if you want to generate this data, this will be a lot more difficult than the say R, E, U, A, O than the vowels part. Right? Generating consonant is quite difficult here. This is the research work from Professor Ishu that I work with in UCL. He proposed the structure of syllables to be constructed of these parts. We have the initial consonant, which occurring at the same time as the vowel, and then we have final consonant afterward. Like when we, if I were to pronounce the word ngan, right? The word ngan, or other word man, right? Man, not title. What? Man, m, and n, right? But the final consonant is like at the end, the n sound at the end. It would not overlap with the vowel, but the m sound at the beginning overlap with the vowel, so that's why you get ma and n, get man. And then on top of that, we have this tone. Right? Tone is a component in the syllables, particularly for not particularly, I would say, especially for tonal language, right? Especially for the tonal language. But in English, which is the stress time language, well, usually back then, I would say back then, now the boundaries are quite blurred, but back then, phonetician linguists classify the language into stress time and tonal. When you want to compare, say, Mandarin Chinese to English, English is stress time. That is, you try to place the stress location on different time. And for Mandarin Chinese and Thai and Vietnamese, these are tonal languages, which means that for each syllable, there would be tone associating with the syllable. Say, man, right? Or ma, ka. These are the tones, right? But for English, you got something like present, different placement of the stress. Right, so these are like the structure of the syllable proposed by Professor Ishu in 2006. And it's good to see, to understand, say, the structure of the pronunciation that we have here. Also, another component of speech that is worth analyzing is the F0, the fundamental frequency. We can see that once we zoom into let's say into just a few 10 milliseconds, let's say this one is 100 millisecond window, what we can see is the periodicity of the speech sound, that it repeats the pattern. But if you were to measure the time period and convert it into the frequency calculation at each time point, at each interval, what we got here is 127 Hertz. Now, just a few milliseconds apart, we got 134 and then 139, right? 139, which means the frequency increase over time, and it can also decrease over time. F0, this F0, or F0 stand for, actually you learn this in physics, in wave theory, I think. F0 stand for fundamental frequency. A nickname in speech, in the audio world, is called the pitch, right? The pitch of the sounds. Okay, so it changed by time, and that is why when we pronounce the word ma, right, actually, if you were to observe the word closely, the word ma, and to pronounce ma, you have to got to the low first and then go up to the high to get the word ma, right? So there are certain variations in F0 in the fundamental frequency signals that we control. This is my dissertation, my doctoral PhD dissertation, which is to create the model of this fundamental frequency. Okay. Right, so it changed by time. And when you pronounce a sentence like แม่มาหานะ not แม่มาหามาแม่มาหานะ this is like this is a very deliberate pronunciation which occupy like 2 seconds long.
แม่มาหานะ
And if we extract those interval out, there's an algorithm to do that, which you have to write them. An algorithm to do that, to extract the pitch, the fundamental frequency out, and plot them by time. We will get this curve. Yeah, I use a software Pratt to extract pitch, the fundamental frequency out of this pitch sound. So แม่ look like this. Right? In the word แม่ it looks like this. About this point, แม่. So and ma, ha, na. So before we continue further, you may argue in your head, because you may be a perfect Thai learner. It is very difficult when you learn the sounds pronunciation and do research like me. I have to teach my son to pronounce, to learn to pronounce Thai word, because there are rules on there. Like we have different like high consonant, mid consonant, low consonant, and then they were pronounced differently. But you know that if it is the aspects of sounds, in terms of tone, you have 5 tone. Either is whether you talk about dor dek, dor shada is also the same consonant, right? So what I want to tell you here is that although the m sounds is not in the mid consonant, which can be which have 5 variations of tone forms, but you can always pronounce the sounds with 5 distinguished variation, right? 5 tones, right? With 5 tone. The mid tone, สามัญ tone, right? Actually that's what I named it. The low tone, because it's go lower. The first tone, เอก right? And actually it's the first tone, that's why it's called เอก right? And the second tone, the to, and 3 the third tone, and the fourth tone, right? I named them in my work to the pattern here. So แม่ here has the pattern of falling. I actually call this the falling tone, and ma is actually the mid tone, because it's kind of reached the mid here. If you want to read my dissertation, I can share that with you. And the rising tone, ha, and na is the high tone. But never mind on my dissertation. What I want to show you here is that there is an F0 contours. This F0 contour is the change of the fundamental frequency by time. All right, let's go on. Okay, and this is also quite fascinating, and it is very difficult to generate in computer even now. This is in terms of voice quality, right? The voice quality, different voice quality would sound differently, and we human can perceive those with different expression. Just try to listen of the male and the female at different voice quality, from modal, normal, tense, just like the word said, you are tense, and creaky. This is modal.
She's thinner than I am.
Female, modal.
You will lay a railway.
This is the modal sound. The tense sound.
Only lawyers love millionaires.
The tense female.
This was easy for us.
This is a tense sound. How does that occur? In many situations, it may occur when the speaker try to get the retort to pronounce it in very squeezed, flat voice. Right, that's the tense one. This is the creaky sound.
Swing your arm as high as you can.
Well, when you go low, so try to speak with the low sounds, or sometimes when you listen to singing, you might hear this creaky voice.
Why yell or worry over silly items?
And it happens a lot. Maybe you are not well, and then you got creaky voice, but sometimes the creaky voice come intentionally, right? Like I'm trying to going low. Then when I'm trying to going low with my voice, the vibration would kind of fall apart, and that's why it creates the creaky voice. But if I were to speak normally, that would not occur, right? So this is the creaky voice and the harsh voice.
A roll of wire lay near the wall.
This was easy for us.
This is a harsh voice, and you can perceive that to associate with something like furious emotion, right? Angry emotion, or something like that. But that is the voice quality that you hear there. And this is falsetto.
This was easy for us.
They may earn more money by working hard.
Yeah, falsetto. And the breathy voice.
He will allow a rare lie.
This was easy for us.
Right? Different voice carry different expression, different emotion, and also it carry different voice quality, which are not present in the spectrum per se, right? In order to generate this voice quality, you need to, well, there are like the active research right now that are trying to produce this. So if we were to compare spectrum between the breathy voice in whispers and modal voice, in the modal voice you can clearly see the spectral peak, the spectral energy, because the vibration of vocal folds are successful. But in whisper, like if I were to whisper this word, modal versus breathy, like this, there's no vibration happen, but you can still hear. Right? Did you? Hopefully this is good enough to hear the whispers. And if we analyze the spectrum between modal and whisper, the whisper sounds would not have the obvious energy in those bands, although you still can perceive them a bit. And you can also see the scattering of energy, which indicate the noise that occur here. Okay, comparing in that is the comparison in frequency domain. In time domain, this is the modal voice have it has the structure. This is the breathy voice, right? I don't remember these two though. This is linear. LPC is the LPC coding, probably, to analyze the magnitude at specific point, LP residue, the remaining after fitting to the model. But I don't remember the EGG. This probably the measurement in the, let me search. I think it's probably the measurement before glottal pulse. I think it should be something related to glottal pulse. The EGG signal is the glottography. Yeah, the EGG signal, electroglottographic, digital version of electroglottographic. There are equipments that you can insert into your into vocal apparatus. Actually, speech researchers back then, when they gather data, they need to kind of stick the sensor into your mouth, sometime inside, in order to measure the data coming out of that. Nowadays, things become better. Instead of collecting the EGG signal, they collect the EMG, the electro EMG, right? I don't remember the whole name. It's like the scan. They collect it as the scan of the signal by measuring the by kind of putting sensor not inside but scanning instead. So there's periodicity in the EGG data and in the speech waveform. For modal and breathy, just take a look at the tense and the harsh. The tense time domain contains a lot of vibration. In the inside structure though, this is not like the zooming out. This is just inside the structure. There are vibration in the tense space. In the harsh space, those vibrations occur only on some of the peak. Right? So these are the voice quality that are in the speech signal. Okay. Do you have any questions about the first part first? Those are about speech signals. Oh, yeah, we do have 2 questions. I just saw that. The first questions, what does black and white part of spectrum mean? This black and white part, right? It depends on the software. The part that I use, the white part represent low value. The black part represent high value. If you use Audacity, then it is another software recording, a free software for audio recording. It uses the tone, the color to denote, like if I remember correctly, black or red as low value and bright value, like bright red for high value. Right. So I suppose this should answer your question. Right. Another question, I would like to know that are there any quantitative studies of voice quality, such as physical simulation, theoretical simulation? Sure, there is. There are research on this, and there are research on the generation of this as well. I would suggest that look at the, just go to Google Scholar and then try to search for the paper. Use the terms voice quality and maybe modal breathy and then the model. If you want to know whether there are certain deep learning models that is used to model something like this, search deep learning and then see if there are works out. But there are for sure, because the one that I showed you, there are phonetic studies back then, but there are lots of progress in the past 10 years in speech synthesis, particularly in speech modeling, in conjunction with the deep learning to create something like generative model. Okay. All right. Let's take 10 minutes break. Right? And afterward, we will now switch from being computer engineer to be say science students studying human anatomy, right? Particularly for speech production. I have a nice book. It's probably I left it at the university. I bought that book when I was a PhD student. It is the anatomy book that contains like the anatomy of speech apparatus and how each sound is produced. Very nice one, which will kind of outlining the way and the basic understanding of speech production. Once you know those components, then you can think of a way to represent the generation process afterward. Okay, right, let's take 10 minutes break. We will come back on 7:35. All right. The next topic of today's lecture is about anatomy and anatomy of speech production systems, which will make us understand different components in how we speak. Okay, let's start. First, I'd like to show you this figure. This is the illustration of human speech production organs, the apparatus associated with speech production. We have this starting from down here. This is the diaphragm down here. Then inside we have the lung and the trachea. The trachea connecting up to this cavity. The trachea, and beside the trachea is the esophagus. This esophagus is the tube that carrying food, right, to the stomach. The lung though has different tube. This is the trachea tube, and this connect to the larynx about here, and the cavity. The cavity in here is controlled by different types of apparatus. Starting from the outside, starting from the thing that is visible, the jaw. We have the jaw here, and the lips and the teeth inside. These are, and the jaw control the opening, the lips control the surrounding, which we associate with the sound coming out. The opening of the jaw will inadvertently associate with the controlling of the cavity inside the mouth. While inside we have a very impressive device called the tongue. We can speak like this thanks to the flexibility of the tongue. With the tongue, we can control. You can try flexing your tongue. You can control the tongue tip. You can control the tongue body. You can raise the tongue back. You can fold the tongue. You can do a lot of things with the tongue. To control the cavity inside the mouth. With different shape of the cavity inside the mouth comes with different sounds that we can produce. In couple with the fine control of the velum inside. Velum is just a muscles that open and close and control the connection between the nasal cavity and the oral cavity. So sometimes you got the phlegm and drift through the velum to the throat, and maybe cause the infection down in the throat as well when you got cold and you got flu, right? So there are connections between the nasal cavity and the oral cavity. All right, and the larynx here is not fixed position. If you when you speak, try to touch here, and when you're speaking, you can see that the larynx actually move, right? It actually move up and down, and that is automatic. when you speak. It moves up to kind of creating less area, reducing the volume in the cavity here. And sometimes you even control this. You even control around this region, in order to produce sounds like go. Like when you pronounce the word go, the constriction actually occur inside the go, and it is actually quite fascinating. It has the first letter in Thai as well. It is constriction about this point, in contrast to something like the or. There's no constriction when you try to pronounce those sounds. So these are the speech apparatus that we control. Okay, did I miss any things here? Okay, let's start from bottom up. Start from the lung, right? The lung, as in biology, you know that the lung is the organ that exchange oxygen with carbon dioxide in the blood, right? The blood has to go through the lung in order to replenish the oxygen inside the blood. And COVID-19 is lung and respiratory infection, which can cause infection in the lung region. That's COVID-19. And actually the infection kind of make the cells become unrecognizable actually recognized as a threat by the immune system. So the lung is actually damaged from the attack from the immune system to the tissue, and that is actually our body trying to destroy itself literally. So in terms of speaking, the lung would have to be when you inhale and exhale, right? The lung will change. There will be air inside. Besides breathing, you can also perform other tasks like pushing those air out and then causing vibration to generate sound. How do you control the lung? How do you think you control the lung? Do you control the muscle in the lung? Probably not. The way that you control the movement in the lung is actually by enlarging the cavity or compressing the cavity through the control of diaphragm. Right? The diaphragm around your lung region. When you kind of increase the volume, by increasing the volume, you decrease the pressure, and that causes air to flow in. And also, when you kind of compress it, the air would flow out. So that is the muscle control that we have. That's why when you got like muscle ache about the diaphragm region, it will be really hard to breathe. So the lung. Then the bronchi, the bronchi connect to trachea, and then connect to larynx. So the bronchi, and it connect to the trachea, and then connect to the larynx here. This would carry the air from the lung inside and out. Right, beside the trachea, there is this esophagus. The esophagus is the pipe connecting. When you eat food, it go down esophagus down to the stomach. Okay. This is tube in esophagus. This is the trachea, and then going down to the lung there. Okay. So in the trachea here, there is a very impressive set of muscle that is evolved and then allow us to speak. And that is called, this is the larynx. In the larynx here, larynx consists of the cartilage and muscle. It's a combination of cartilage and muscle. Here is this cartilage about this. And then we have like muscle. This is the a ligament, and there are certain muscle membrane here. And there are certain important, sorry, there's some insects here. Important muscle groups that control the the air that's coming out, right? This is called the vocal fold, right? This vocal fold is a set of muscle that would be tense when you want to speak, and when it is tense, when they are tense and the air blowing out, there will be vibration occurring. This vibration creates the sounds that we hear here. So I have video showing you that about how it vibrates. It's actually like when you're trying to constrict, not letting the water flowing to the slit, you kind of close it. But when there is a pressure building up, and it has to open. And with the pressure reduced, it can close again, and then it open and then close. This is how it works, the vocal fold. The tension occurs from the control of the cricothyroid and thyroarytenoid. These are the muscles. The thyroarytenoids mean the thyroid and the arytenoid muscles about here. And the cricothyroid is there is a cricoid joint, cricoid cartilage, the cricoid cartilage here, and there are like cricothyroid muscles, which when they are like tense, become active, it would generate the tension in this vocal fold, and then when the air blowing up to the trachea, it would kind of control the vibration, create the vibration there. Right. So the combination, if we were to think of it in a simple term, right, the speech production consists of the control of the vibration at the vocal fold and the shaping of the cavity in vocal tract. Vocal tract consists of oral tract here and the nasal tract. The oral tract are controlled by tongue, teeth, lots of equipment there. Velum. The vocal fold is controlled by the tension that you put in order to make the sounds have higher note or lower note, having high sounds or low sound. Okay, so how does it work? How is the speech sound generated? So it starts by blowing airflow, the flow of air from the lung. This airflow would pass through larynx, would vibrate. Certain vibration occur at the larynx. Just imagine, actually, if we think about airflow, it will just flow through, right? But once it's past the constriction, it would generate a pulse. Usually this is called glottal pulse because it passed through the glottis, passed through this larynx region. And then after passing through, it generates a pulse of air. And this pulse of air would be resonated in the vocal tract. And then we create an obstruction of the sound using teeth, tongue, lips, velum in order to generate different sounds. Velum connect to the nasal tract. And in speech perception, we hear it through the outer ear, and this is the ear canal, and we got this different steps, the malleus, incus, and stapes. These are the cartilage in the ear that would kind of trigger or carrying or vibrating once the sounds come in, and this would propagate through the liquid inside the cochlea, which we have the hair. We actually have hairs in this region in order to sense different frequency in the vibration. Okay, so the sound waves vibrate eardrum and cause fluid in cochlea to vibrate as well. And then there will be they would vibrate the hairs inside cochlea, and a different frequency would trigger different hairs. And this would convert it into, this is a way that is converted from time domain to frequency domain using our ears. Okay, so that is in the overview of speech production perception in a simple term. Now, there are modes in speech production equipments because the organ that I'm talking about is not used solely for speech production, right? We use these organs to perform respiration, to breathe. We use them to create a phonation, right? To generate sounds, and we also use them to articulate. Articulate means you are controlling the sounds that is coming out. In order to do all these things, there has to be a center of commands to instruct us to control different muscles to do different tasks. For example, I'm talking while breathing at the same time, right? So respiration has to work, all the three has to work together. Sometimes I need to breathing in, and then I'm speaking. So I need to kind of have the motor to remember how to do this. This is also probably if somebody has not speak in public, or it has not speak continuously or practice doing that, it would be a little bit difficult to do that because your brain has to remember the controlling pattern, just like driving. Your brain has to remember the controlling patterns that it needs to instruct our lung, our speech apparatus to work together. And this is at the motor level. Usually it's called the motor cortex. And the cortical level is like the one that about consciousness and the other, but the motor level control how we speak. Okay, now let's take a look at these three modes, and that's it for today. Let's take a look at these three modes of speaking, these three modes of controlling the speech production. First, breathing, right? Breathing, well, you know what is breathing, right? We have to do it since our birth until our death. Respiration has to be done. You cannot just try just to think that let's hold your breath for a few seconds and then you will know what breathing is. Don't do that. I don't want you to die, right? Respiration and breathing are usually the process of exchanging gas, exchanging air of the organism with the environment. Different organisms, different beings would have different ways to exchange to breath. Okay, so for human, we breathe by using we are breathing by using Boyle's law. This one is like since the high school, like P1V1 equal P2V2. If we increase volume to maintain this, if we increase volume, pressure would be dropped, and that would cause the air to flow in, right? So when we speak, there are certain patterns. This is the study of breathing that has been done back then. There are certain level of breathing, right? This is like if we think about the whole thing here as the total lung volume, the inspiration volume. This is the inspiratory volume, and when you breathing in, inhale deeply, this is the volume of air in the lung would increase to a certain level. When you exhale out, it continuously going low here, right? This is when at rest nothing happens. When you try to breathe quietly, we have this as the tidal volume, like the volume of air that would go in and out, like when I'm speaking here. When you try to force inhale, you inhale to a certain extent that you cannot inhale anymore, and that is the reserve volume. We have this as the reserve volume of air coming in. The good swimmer would have like large reserve volume so that he or she doesn't have to, or good diver doesn't have to, can use like low oxygen there. And then the tidal volume here is the volume that need to keep in order to maintaining that. And if you were to force exhale until you cannot, and that would be the the expiratory reserve volume, the volume of the exhalation that you kind of you can go down to that level, and there will be a certain residue volume that you cannot really exhale it out because of the atmospheric pressure, because of lots of things. So we have this as the inspiratory capacity, the capacity to inhale, and down here is the functional residue capacity, the capacity and the residue to do the function that you want to do, like speak without taking a breath, or in singer, for singer, they need to have like large amount of this functional residue capacity. Okay, so this is the breathing, right? It can be used to assess the ability to talk and the ability to control. And actually, by controlling this breathing pattern, you can perform different tasks. You can like do the speaking like this one. Well, it's not like if you control this breathing pattern, you can use different set of movement like in Yaiba. Right? Okay, the lung volume, the lung volume is also different when you have different body orientation. The best lung volume, the highest lung volume that can happen is when you are standing. Okay, you have the highest lung capacity to do the job. This is probably because of gravity. Right? When we are standing, the gravity going down does not hinder us in controlling the diaphragm movement, and that also doesn't hinder us in inhalation or exhalation. On the contrary, if your body orientation looks like this will be the hardest point to speak. Sitting has a less effect than standing. So I don't know why they try to measure at this point though. Well, at this level. Okay. So it means that standing up and talking is the best. Okay. This is a real scientific study, not a joke. Okay. So if we were to measure the pressure, right, that is called the alveolar and intrathoracic pressure. The pressure inside, right? The pressure inside. On inspiration and expiration, inhalation and exhalation. Then there will be the fluctuation in the atmosphere, in the pressure and the airflow, which is obvious. When there is airflow, high airflow, airflow going out, in inspiration, airflow going in, in expiration, airflow going out. so just tell you that there's pressure different. Okay, now in speech production, we can think of the lung as the source that provide the energy for speech. So if you want to be a good speaker, right, you need to control the inhalation, control your breathing. If you can control your breathing, then you can control the way that you speak, because it's the source of your speech. Because how does it work? Because it supply the whole system with airflows. We need airflow. So we need to have air flowing to the systems in order to generate the sounds. Okay, that is breathing. The next is phonation, right? Phonation is just like in electric analogy. If we think about lung as a source of energy, then as a power supply, then the phonation is the vibrating elements. Is the component that generate pulse, that generate the clock, that generate vibration. And then we will have a system of valve that allowing this vibration to go out or go on the way that we want. So in this energy, which will be in forms of the airflow, the pressure from the lung, will be modulated, right? Will be modulated at the larynx. What does it mean by modulated? It's like if we were to just breathing, inhaling and exhaling. There's no obstruction, right? If you touch your neck while during inhalation, you will not feel any vibration at all, right? But if instead of just exhale or inhale, right? If we do the opposite, if we were to speaking while touching, then you will feel vibration that occurs at the larynx. This is the main structure that create vibration, but it is not the larynx per se. Larynx is like the whole thing, like the external structure protecting what is inside. That is the most important, and that is the vocal fold. Before a proper imaging, people call this a vocal cord, right? Just like something like we have this cord and then it vibrates like guitar, but it's not that. This is a vocal fold. We have a pair of muscle, this pair of muscle that can become tense. Once it becomes tense, it can vibrate. Just like when you speak R word, we can when you speak R word, you actually generate the vibration, right? The vibration that with your tongue. But instead of that, we can control our vocal fold. Our vocal just will vibrate, and this rapid opening and closing of the vocal fold interrupt the stream of air, and then let it go and interrupt it again, and keep doing that at the constant interval. And that is why we see periodicity in the speech signal. And those pulses will then be shaped by the cavity in our mouth. Okay, this is the frontal section of the larynx. So it's like this is me, right? Say if you were to cut this and then just will the larynx at this position, just cut it and then view the frontal section of the larynx. It would look like this. These are the larynx, what is called the true vocal fold, right? The true vocal fold. And we have the above is epiglottis, beyond glottis, right? And then we have this muscle. This is the thyroid cartilage. You may have heard the thyroid gland around that cartilage. There is a cartilage around that. กระดูกอ่อน right? Yeah, cartilage. And then there is this cricoid cartilage. This is a thyroid gland. Cricoid cartilage. This muscle is controlled by this the strengthen, right? The cricoarytenoid is about here, and this is the thyroid. It's controlled by this cartilage, and this become tense. It vibrate. These are pictures taken during different modes of breathing and phonation. During quiet breathing, we see something like this. Back then, people thought that these are the chords that vibrate, but no, these are just the fold of muscle. Quietly vibrating, we would have like in quietly breathing, the slit would be quite wide, but not that wide compared to forced inhalation. Doing this, the vocal fold will be kind of far apart. So you can think about when you have problems with breathing, it's probably something that related to this muscle, maybe. In whispering, this is just like quiet breathing, but in phonation, this muscle become tense, and then the slit is closed, and the phonation during normal phonation it looks like this. I have animation that will show you on the right hand side here. That will show you the movement of this vocal fold vibration. So the muscle is from the start, it would kind of open up, and then open, and then close. And then this occur within, just imagine, just a few milliseconds, like 10 milliseconds, it open and close very fast. Yeah, it open and close very fast. That happen in our trachea all the time that you speak. Just 10 milliseconds, and it open and close. Imagine that. So this principle is actually just like when you have constriction in Pracha Utit Road and a few cars can pass by. So what happened is that the pressure would be building up. So it's just like this one. Yeah, the pressure building up until it wins, and then it opens until and when once it's open, the pressure down here reduce. So the muscle close again, and then pressure building up, and then you keep going all the time that I'm speaking like this. Okay. Now you may have seen movies that, especially the villain, some people use this device that they kind of put into the device that they just put into their neck in order to make them able to speak. And that device is the modulator. It actually creates vibration so that you can control your speech apparatus. Even though you have that, there might be like infection, or that patient might have the vocal fold removed for some problems. And using that vibration, people can speak normally, right? Speak normally with that device. Okay, and the vibration here generate the airflow out of the vocal fold. This is called the Bernoulli effect. Right? The Bernoulli effects occur in many things. Like, just think about, you have a straw, and then the liquid going up, coming out as the drop of water. Again, it's going in the drop of water. And that is also something similar to this as well, right? So many phenomenon has this Bernoulli effects. So try to feel your vocal fold. Just put your hand to your throat and take a deep breath. You wouldn't feel any vibration in breathing. But let's say out loud. Well, this is okay, that's clipping that. But in if we were to, it would be fun at the university, right? Because everyone will say right? Say out loud and you feel vibration, or just talking and then you feel vibration occurring at this. Let's try touching the cartilage that covering it. You feel vibration much more than the other. Now you can try whispering. Whisper something like, "I like speech processing," like that, and then you wouldn't feel any vibration at all. Right? So that is the vocal fold at work. Thing, yeah, I already have explained. How does it happen? Take a deep breath. Nothing happened because air just flow through, no vibration. Say or say ooh, e. Certainly there's a vibration. But how about s? No vibration. If you speak the word s or f, sh, there's no vibration. Or when you whisper, hello, no vibration. Yeah, because we can generate speech differently actually. Some of the sounds are generated from aerodynamics, some from vibration, and we did that automatically. Quite amazing. The one pulse here is called the glottal pulse. The glottal pulse, because actually the whole thing here is called the glottis. The glottal pulse. The glottal pulse has certain area here, and this pulse would be later shaped into the complex pulse that we saw. Okay, so it has about 50% of opening phase, and then about 40% of closing phase, and then the closed phase, and then repeat the pattern again. The vibration of vocal fold has been modeled using the spring mass model. This is the spring mass model by Flanagan in 1967, and then later Ishizaki and Flanagan proposed this the 2 degree of freedom, the 3 mass models, that they are actually the 2 mass with the damper, spring damper models. So there might be, let's say there are multiple actors in place that control the vibrations. My thesis, actually I should put my thesis into the slide as well. My thesis is to translate this to mathematical model, because we know that there has to be like 3 or 4 sources involving with controlling the vocal fold tension. So I propose that we can use linear model, like linear equation, with the target driving force to represent the signal, the pitch that coming out here. I will show you that in the pitch extraction lectures. Okay, so after the glottal flow coming out, it would pass through the cavity, and then at the end, the output from the lips would look like this one, which is totally different from the glottal flow. How does it work? It works by because this glottal flow would have the spectrum that looks like this. If we were to multiply this spectrum with the filter that emphasizes some frequency, just multiply them just like in filtering, multiply them, then the output would be the spectrum that has certain high frequency on some frequency that is shaped by the vocal tract. This is the way of speech production. By means of shaping frequency, the vocal tract control the resonance process, and the final sound is radiated from the lips. So it's like this. We have lung as airflow passing to vocal flow. We have glottal flow passing to vocal tract. We got speech, and that comes from resonance. These are the forming frequency of the resonance process. Okay, so that is phonation. The last one, before we take a break for tonight, is articulation. After you generate the glottal pulse passing through here, we now have glottal pulse, and it has to go to do the resonance. In order to fluently speaking the things that you want to speak, you need to articulate, control the speech apparatus to form the shape that you want. That is called articulation. Right? Articulation is a process of adjusting the shape of vocal tract so that you got the sounds that you want. Okay, if I were to teach you thinking, this would be different, or teach you speaking. Sometimes in learning to speak English, teacher would ask you to articulate clearly, that use the consonant clearly, so that it would be the sounds that you want. For Thai, we do that automatically. But some people, even for Thai, they would just, the word is quite slur. That's just because of the articulation. If it's not purposeful, articulation would not be heard. If it's not clear enough, it would be hard to hear. So in articulation, the structure of apparatus that related to speaking here, they are called articulators. The tongue, the lips, the velum, these are all articulators. Articulators control the vocal tract cavity. So if you just look if you are in front of the mirror and then look inside your mouth, you see This is tonsin, ula here, not related to speaking, but it's there. And these you have this soft palate, which when you just try to feel it, put your tongue inside your mouth a bit, and then you will feel, you will see that there are certain soft region inside your mouth, inside. And then there will be hard region, the ridge. We call that the hard palate. When you pronounce the word t, that is when you use the hard palate, by putting the tongue to the hard palate, the t. But the ng, and that is using the middle of the tongue to push into the soft palate of your mouth. And there are these are the more detail, the vocal tract and the nasal tract. I already showed you this figure. Yeah, the vocal tract. So what are the articulators related to this? We have this alveolar ridge. Alveolar refer to the ridge on the hard palate. Try to feel it. Everyone has that. The ridge here before the teeth, before your front teeth. Human anatomy. And the hard palate, the soft palate is inside. Ula is inside here. We have this tongue root, tongue body, tongue blade, tongue tip, which we can control with a high degree of freedom. And that's why my work right now is on high quality speech synthesis, which is to simulate the whole thing. It's quite difficult. Okay, but yeah, this is the vocal tract, and we as human has actually quite a nice system built in and control that. Modeling it computationally, we can model lung airflow supply, vocal fold, vibrating, generating this voice source spectrum, look like this. This voice source spectrum then pass through the vocal tract, act as resonator. This vocal tract would have the frequency response that emphasize some of the frequency. And through the process of, if you study signal before, there's a process called convolution. Right? Convolution is just like when we have a picture and then you want to blur the picture. You put in the mask, certain mask, to do convolution, the filter, and then you got the blur picture. That's the convolution or filtering process. And that is done in time domain or in spatial domain by multiplying and then moving. In frequency domain, if you got the spectrum, the Fourier spectrum, in frequency domain, convolution in frequency domain is the multiplication of the spectrum. So you multiply the signal here in the frequency domain with the frequency response. And this frequency response would kind of emphasize some of the sound. It's just like when you're shopping for headphones, right? When you're shopping for headphones, there will be this curve frequency response, which will tell you which frequency will be emphasized. The same things, right? So and then you got the sound output. So just like this picture. So the process, in a simple term, is like you got this glottal pulse, which in the spectrum look like this one. And what is this? This is the frequency at the fundamental frequency, at first harmonic and another. So you got this frequency component of this glottal airflow. This glottal airflow has this spectrum, and then once it multiply with the frequency response of the cavity, you got this spectrum of the output coming out of the mouth. And this is like musical instrument. It's like the violin. Every musical instrument has cavity, right? Yeah, every one of them. Or it would have certain equipments that it would have certain occasion that generates cavities. Violin has the cavity inside, and the quality of the sound coming out depends on the wood, depends on the string, depends on lots of things that revolving with the vibration of the sound and the resonance of the sounds. The expensive grand piano would have a large chamber for the resonance to generate. The flute, clarinet, oboe, piccolo have different shape. It has different. It would have different shape in the end, at the middle, at the beginning, in order to generate different sounds to come out there. Okay, so there's this link. You can listen to that later. It's just to allow you to listen to different sounds. Yeah, but we probably won't go there here. You can try to listen to this later on. Okay, now let's talk. Those are for musical instrument. They will generate different spectrum. Now for speech, the R speech, this is the mouth. R speech would have the high opening, right? The large opening for the mouth, but we would have like stricter inside the R. And the R, like in father, has the high peak at about 800 and 1000 here. This is F1, first formant, second formant, and the third formant around 2500 Hertz. The E, like in heat here, has the first formant about less than 500, maybe 300. And then the second one at about 2300 and about 3300. This is for heat. And for pool, the U, for heat, when you try to pronounce heat, you are actually creating a constriction in this region. This is the tongue center. But inside, it will be wide open for heat. For pool, you are creating like a constriction in the end and down here, but there is like an opening about the end for pool. And this would generate the first and the second formants less than 1000 Hertz, and the third formant around 2500 Hertz. Now this is my recording of E, U, and R. Right? And you can see the R occur here. Right? And just like this one, R, 1000 Hertz. This is from the book called A Course in, not in Data Science, A Course in Phonetics, the reference book that I gave you that, I think. Did I give you? Yeah, it's called A Course in Phonetics by Peter Ladefoged. He's the father of the field from abroad. That is the father of the phonetics field. Right? That is the book is called A Course in Phonetics. I got one, but I think I lent it to some students. I forgot to ask to return. Don't know where it is right now. Have to find it. This is a very classic book that I really need to collect. And then this is from the book, and then I compare that to the actual thing here. So this is R, about 1000 Hertz. You can see F1 and F2 here. For the U here, the pool, U is about here, and the E is about here. This is for E, 2000 something and something less than 1000. Right. So the energy of the spectrum would occupy those regions. So the radiation spectrum, if we were to look at different vowels, would radiate differently. Like for this heat, we have these patterns of high energy of less than 500 and then 1700 something. For heat, it sounds like heat and heat, but the second and the third formant will be closer together. For the heat, this is similar to heat. It has shorter vowel, right? But you can see the spectrum are quite similar. For hat, this is different than the rest, than the three. Yeah, and for the other as well, this is for haw, right? For haw, for hood, for hot, and who. The radiation spectrum would be different depending on the vowels. Why is that happening? This is because just like in in the experiment, if you in the musical instrument, if you create constriction, right? If you create constriction at different point, this constriction would generate different resonance frequency. When you have, if you think about the lips, this is the lips, back into the glottis like this tube. If this tube is compressed about this region, then we got this resonance frequency. If it is compressed like in U, there is the constriction at the end and the constriction at the beginning, we get this pattern. And if it is shorter and it is longer, then we also have different relative frequency at different location. Okay, that means actually this is interesting. I heard, I listened to hear this from a study of the red deer. Right, the red deer is a type of deer that when it wants to announce its presence and want to communicate with to the female, right, to show that its prowess, it would lower the larynx, right? Lower the larynx from the usual location down to the stomach. It can lower the larynx down and to generate the deeper sounds and to be more attractive. And that is actually the probably the psychoacoustic theory of the attractiveness with the sounds. Right? You can try to search that. That's the end of today's lecture. Hope you enjoying it. This is the first assignment, assignment 1-1. I break it down because otherwise it might be too much, especially when you just work on this. For this assignment, you need to use the Pratt program to do things. You need to record your own voice, pronouncing different Thai vowels. There are Thai vowels, canonical vowel, R, U, U, E, E, R, O. Right? Just pronouncing them, and then select the voice part of the sounds, calculate the spectrum, and then measure F1 and F2, and then record it. And then try to plot that in scatterplot. Write the report, submit to LAB2. Right. So this is the assignment. I will show you how it works here. Any question first? I'll show you how the Pratt program works and where can you find it. All right. So let me go to Pratt. Just search Google for Pratt, P-R-A-A-T. Right, this is the Pratt program. Pratt is written by Paul Bosma and David Wisnick. They are I would say they are actually computer engineer, software developer that work on phonetics. So they create this software for phonetician to be able to perform phonetic study without really need to write their own program, right? Which is very nice framework to use. You can download the whatever Macintosh or Windows version. Don't need to install them. Just unzip the package, and then you can just use the program as is. It has already been compiled. So I already did that. So I'm going to open the program to show you here. Here is Pratt. I did share the screen, but it hasn't come up yet. Okay. This is the program. We will talk about the deadline later. I will demonstrate this to you first. It seems that it's too small. Let me share this in the advanced way. Portion of the screen. Okay, good. Okay, this is Pratt, just a simple program. Unzip it and then you get the Pratt program, just run it. It contains the menu here. This is the object window and the picture window. So in the object window, you can record the sound. Let's say I will record the sound, mono sound here. It will pop up this. Let's wait for it. Oh yeah, it will pop up this screen out. This is the sound recorder, and this you can control the sampling frequency and the channel that you want to record. The microphone here is mono, so I'm going to record it mono here, and then here is the record button. Just push it, and then yeah, you're recording it. E, U, for example. And then once you click stop, you can click save to the list and close. Yeah. And then you will get this sound untitled. From this, you can actually click edit, and then it will show you the different part of the sound. It will show you this. It will show you this dialog box, which will show you the time domain and the frequency domain of the sound. If you want to zoom in, I think just highlight some part of that, and then click. This is the zoom in, out, and selected, and then click selected, and then it will just zoom into just that portion of the sound. Now what I ask you to do is to just selecting some part of the sound, and if you click all, then it will just zoom out. Just click, you can just zoom to the selected here, and then just click on the voice part of the sound. This is for R, just a few here, and then click the spectrum, and you can view the spectral slice, which means that the Pratt will use the selection here to plot the spectrum of this slice, of the spectrum of this slice of data. And here is the spectrum. From here, you can measure the peak. Just click on some point. You will see that this is 700, 800 Hertz, and something like 3,600 Hertz. Okay, this is for the R. Yes, some. Do you see the lagging in Zoom? Because it seems like when I share the whole screen, it is quite lagging here. The video is not lagging though, but the screen sharing is lagging. Never mind. So this is how you can do the assignments. Now let's talk about the deadline. Let's go back to the slide. Probably should need to, and then talk about the deadline. When do you want to submit your work? I'll check the schedule. It should take about 1 week to do this, but if you need 2 weeks, then it's fine. But 1 week, I think 1 week should do. What do you think? I'm okay with 2 weeks though, if you want. One or two. I I'm quite open with the deadline that you choose. Yeah, your friend said, yeah, Sanchanok said, I prefer 2 weeks. I'm okay. Everyone's, what do you think? 2 weeks? Just submit the work before 2 weeks, let's say. If you finish in 1 week, just use 1 week. Just before 2 weeks, do the work, and then it would take like just 1 hour to do that, right? So just do the work and submit the work within 2 weeks. I will create a submission slot onto LEB2, so you can submit your work there. Okay. That's it. That is the topics for today. I hope that from this lecture you grasp more concept of speech production. You will see how the speech signal is generated. And once you learn further, you will see that a lot of technique that try to analyze speech utilize these concepts of speech productions and perceptions to create a measurement, to create a features and attributes that could capture different parts of the speech. Okay. Any question that you would like to ask? All right. No question. Really? Yeah, just try recording your voice and perform analysis of your voice. This will be fun. Right? Seeing the different frequency occurring when you just pronounce. Students back then, they said that because they do this in the senior project room at the university, and their friends kind of being stunned on what they are really doing, pronouncing the sounds, and then and yeah, some of you will not be will be shy, and yeah, but try to play with this. It's quite fun. You can use Pratt to do the job. There is actually other programs that allow you to work with in Python, but Pratt is simple. Let's just use it here. Later, we will write an algorithm, some of them, to process the speech data. Okay, but for now, in order to study the formants, to understand speech, just use the program here to try to dig in and then understand frequency components in the speech. All right. If there's no more question, let's call it a night, and I'll see you later on the next week. Bye bye.